Noche Cósmica.
Imagine for a moment the sound of nothing. Not the nothing of a quiet room, where the hum of electricity still trembles beneath silence, but the absolute nothing of the vast spaces between stars, a space so empty that light itself takes millions of years to cross it. And yet, in that emptiness, something extraordinary is listening. Something is gathering. Roughly 2 billion light-years away from where you rest, structures so immense they defy the language we use to describe size are slowly, patiently assembling themselves into configurations that may persist for trillions of years. These are galaxy clusters, not scattered islands of stars drifting randomly through the cosmos, but the largest gravitationally bound collections of matter in the entire universe. Each one contains hundreds, sometimes thousands of entire galaxies, bound together in a cosmic embrace so powerful that nothing can ever escape. This is where our journey begins, in the patient, unhurried dance of structures so vast that the number of stars within them exceeds the total number of grains of sand on every beach on Earth, many times over. For those drawn to the quieter mysteries of the universe, to the stories of cosmic assembly, told at a pace that mirrors the patience of deep time itself, consider subscribing to explore more of these slow, unfolding revelations about galaxy clusters. These are journeys through scales that challenge the human imagination, through billions of years of cosmic silence, offered at the cadence your mind needs to drift towards sleep. Now, let us venture into that silence. To understand what a galaxy cluster truly is, it helps to begin with a sense of scale layered upon scale. You know the Milky Way, our home, a single galaxy containing roughly 200 to 400 billion stars, orbiting around a supermassive black hole at the galactic center. It is, by any measure, vast. It is also lonely, in a way, or rather, not quite lonely, because nearby are companions. The Andromeda Galaxy, slightly larger than ours, orbits in a mutual gravitational dance alongside the Milky Way and perhaps 50 smaller satellite galaxies. These dozen or so galaxies, loosely bound together, form what we call a galaxy group, a gentle, gravitational family. But a galaxy cluster is something else entirely. Imagine not one Milky Way or one Andromeda, but imagine taking 10,000 galaxies the size of the Milky Way, 10,000, hold that thought, and bind them together with gravity alone, not with walls, not with forces we can see, simply with the invisible, patient pull of one mass upon another, stretched across distances so immense that light itself becomes tired crossing them. That begins to approach the scale of a major galaxy cluster. This is what the universe chose to build. On the largest scales, matter does not scatter evenly. It collects, it pools, it assembles into these vast, slow hierarchies, and the largest hierarchies of all are the galaxy clusters themselves. But here is the question that has haunted astronomers for nearly a century. How did these structures come to be? How did the universe, which began as something almost perfectly smooth, nearly featureless, just slightly warmer in some places than in others, evolve into these towering monuments of matter? What architect drew these blueprints across billions of years? The answer, it turns out, begins with something we cannot see, and it begins very, very early. In the first fraction of a second after the Big Bang, when the universe was unimaginably hot and dense, a process called inflation stretched space itself faster than the speed of light, smoothing out most irregularities. But it did not smooth everything away. Quantum fluctuations, tiny, Heisenberg-born ripples in the fabric of reality itself, were stretched across the entire cosmos. When inflation ended, these ripples remained. They were imprinted into the earliest, most distant echoes of light that we can observe today, the cosmic microwave background. This ancient light, now redshifted to the microwave portion of the spectrum, carries within it a map of the universe's first moments. And if you look closely, if you measure it with exquisite precision, you can see the thumbprints. Regions slightly denser than their surroundings, regions slightly colder, regions slightly warmer, temperature variations measured in millionths of a degree Kelvin. These are the seeds. These gentle undulations in density, no more than 1 part in 100,000 different from perfectly uniform, became the scaffolding on which all structure in the universe would be built. Given time, given gravity, given nearly 14 billion years. In the early universe, a few 100 million years after the Big Bang, something remarkable began to unfold in those regions, marked by slightly higher density. The invisible gravitational pull of dark matter. Matter so strange that we still do not fully understand its nature. Matter that interacts with ordinary matter through gravity alone. This dark matter began to pool. It gathered slowly, imperceptibly, in those regions where quantum fluctuations had tilted the balance ever so slightly toward denser conditions. As dark matter accumulated, it created deeper and deeper gravitational wells. These wells, in turn, began to draw in ordinary matter, the hydrogen and helium gas that filled the early universe. The gas fell inward, it collected, it was compressed, and in the compressed cores of these dark matter structures, the first stars ignited. The first galaxies were born. Picture that moment. The universe is still young, the darkness is profound, and yet in the densest regions, gathered by an invisible architect, the first galaxies flare into existence like distant candles. They cluster together because they were always meant to. They were born in the same pools of dark matter, and those pools were the seeds of the first protoclusters. What an extraordinary thing to contemplate, even now, that in your listening, in this quiet moment, you are being told about structures that began forming when the universe was but a toddler. Structures that have been gathering ever since. Structures that will continue to gather, slowly and in silence, for longer than your mind can hold. The universe, it seems, builds by accumulation, by patience, by the gentle insistence of gravity over unimaginable stretches of time. There is something profoundly settling about the thought of structures so large that our ordinary measures of distance become almost quaint. Galaxy clusters exist at a scale where even light itself, the fastest thing we know, takes millions of years to traverse from one edge to another. And as you listen to this, you might wonder what it would feel like to truly comprehend that distance, to hold in your mind the idea of something so vast that it contains not mere galaxies, but hundreds, sometimes thousands of them, all held in a delicate cosmic embrace that has persisted for billions of years. If you found yourself drawn to these slower explorations of the cosmos, to the kind of unhurried meditation on cosmic structures that unfolds across epochs rather than moments, you might consider joining us in this ongoing journey. We create extended documentaries specifically designed to guide you through the universe at the pace of deep time itself, where rushing has no place, and every detail of how galaxies gather, how they drift in invisible frameworks, and how the cosmos arranges itself on the largest scales becomes a kind of restful contemplation. Each episode drifts through another facet of galaxy clusters, from their hidden architecture to their slow evolution across 13 billion years. There is a particular peace in following these cosmic narratives without haste, in letting the vastness of what these structures represent settle into your awareness the way starlight settles into a patient observer's eye. The beauty of studying galaxy clusters at this slower pace is that it allows you to absorb not just the facts, but the emotional resonance of them. When you learn that your own Milky Way is part of a galaxy cluster, that we are held within a larger family of galaxies all bound by gravity, something shifts in how you perceive your place in the universe. And when you understand that this relationship has shaped our local cosmos for billions of years, that the pull and influence of our neighboring galaxies has gently guided our own trajectory through space, the knowledge becomes less abstract and more intimate. Subscribing means you will have access to future explorations that take this same patient approach, that examine not only what galaxy clusters are, but why understanding them matters, and how they reveal truths about the universe we have never before been able to perceive. The structures we are about to explore together require this kind of unhurried attention. Galaxy clusters cannot be understood in a glance or summarized in a moment. They demand a gradual unfolding, the kind of narrative that gives you time to actually visualize what is being described, to feel the weight of cosmic time, to sense the quiet pull of gravity shaping matter across billions of years. When you join this ongoing collection, you become part of a community of listeners who understand that the cosmos is not meant to be rushed through, that the deepest rest often comes from contemplating the deepest mysteries. Each new episode will take you to another region of this vast web of galaxies, will introduce you to observations made by patient astronomers over decades, and will help you internalize the profound calm that comes from understanding your small place within something genuinely immense. So as we prepare to move deeper into what galaxy clusters actually are, into the mechanisms that gather them and the invisible forces that hold them together, know that this is just the beginning of a slower, longer conversation about the universe's largest structures. What lies ahead is an invitation not simply to listen, but to let your mind drift alongside billions of stars, to feel your breath synchronize with the vast, patient processes by which the cosmos organizes itself. Whether this is your first time exploring these realms, or you have journeyed with us before, the rhythm you are about to enter is one designed to settle you, to teach you, and to remind you that there is infinite calm in contemplating infinity itself. In the quietest corners of the cosmos, where our instruments strain to perceive the faintest signals, there exists a scale of gathering so immense that it seems almost impossible. Imagine, if you will, not one galaxy like our own Milky Way, not even a dozen, but hundreds, sometimes thousands of galaxies drawn together by a single, patient force. This is a galaxy cluster, one of the largest structures the universe has managed to assemble, held in a gentle but relentless gravitational embrace that has endured for billions of years. Now, before we drift deeper into this cosmic architecture, it helps to understand how these clusters differ from their smaller cousins, the galaxy groups. The distinction is quiet but profound. A galaxy group contains anywhere from a handful to perhaps 50 galaxies, all loosely bound together by gravity's whisper. Our own Milky Way belongs to such a group, the local group, we call it, where perhaps 80 galaxies orbit in a slow, unhurried dance with one another. Imagine a small circle of friends gathered in a vast hall, each one aware of the other's presence, each one subtly influenced by the pull of the whole. But a galaxy cluster is something altogether different in scale and character. A typical cluster contains somewhere between 300 and several thousand galaxies, all clustered within a region of space that might stretch across several million light-years. To visualize this, consider that same hall of friends, and then imagine it expanding outward, drawing in more and more companions, until thousands upon thousands of galaxies find themselves woven together in this intricate tapestry of gravity. The sheer number alone changes the nature of what we're observing. It's no longer a gentle gathering. It becomes a gravitationally bound community, a cosmic structure so massive and so tightly interconnected that it remains stable across the entire span of the universe's existence. What makes a cluster truly cohere? What keeps all these thousands of galaxies from simply drifting apart into the expanding void is gravity itself, but not merely the gravity of the galaxies we can see. This is where the picture becomes wonderfully mysterious. When astronomers first began measuring how tightly these clusters held together, calculating the velocities of individual galaxies and the mass those velocities implied, they discovered something that shouldn't exist according to conventional understanding. The clusters seemed far too massive. The visible galaxies, all those stars and dust and light we could detect, simply didn't account for the gravitational pull required to keep the structure intact. There had to be something else, something invisible, something pervasive throughout the cluster, binding it all together. This invisible scaffolding, this hidden architecture of matter, is what we now call dark matter, and its presence within galaxy clusters is so profound that it shapes everything about how these structures behave. The distinction between a group and a cluster, then, is not merely one of numbers. It represents a qualitative shift in how gravity operates at cosmic scales. In a group, individual galaxies maintain more autonomy, more independence. Their velocities are relatively modest, their interactions with one another less intense. In a cluster, the gravitational field becomes all-encompassing, a constant presence that permeates every corner of the structure. Galaxies move more rapidly within clusters, orbiting within a gravity well so deep that escape seems unthinkable. And as we'll discover as our journey continues, this difference in scale and intensity transforms not just the motions of the galaxies themselves, but the entire physics that governs how they interact, merge, and evolve across cosmic time. Consider the calm efficiency of this arrangement. A galaxy cluster represents a kind of cosmic equilibrium, a balance between the outward expansion of space itself and the inward pull of tremendous gravitational forces. Within this equilibrium, thousands of galaxies pursue their slow orbits, sometimes approaching one another, sometimes receding, but always held within the invisible bounds of the cluster's gravitational field. What could seem violent or chaotic from an external perspective becomes, when viewed through the patient lens of cosmic time, something far more like an elegant choreography, a slow, intricate dance that unfolds across millions and billions of years, with each step measured not in days or years, but in epochs. The boundary of a galaxy cluster is itself a subtle thing. Unlike the clear edge of a planetary body, or even a galaxy, a cluster's extent is diffuse, gradual, almost philosophical in nature. The gravitational influence of a cluster extends outward through space, with no sharp demarcation, no moment where one can say with certainty, here the cluster ends and the void begins. Instead, there are concentric zones of increasing distance and decreasing density, a gentle fading of gravitational influence that eventually surrenders to the vast expansion of space itself. This indefiniteness, this softness of boundary, is one of the reasons galaxy clusters are so wondrous to contemplate. They are not fixed, bounded objects in the way we typically understand structures. They are dynamic regions of space, where gravity has won a temporary but stable victory over cosmic expansion, where vast quantities of matter have coalesced into a configuration so enormous and so stable that it will endure for trillions of years. In the beginning, when the universe was barely 380,000 years old, an infant truly, there existed something so subtle, so faint, that it would take humanity 13 billion years and machines of extraordinary sensitivity to even perceive it. The universe at that moment was still glowing, still hot, still filled with a soup of elementary particles and radiant light, so intense that matter itself could not yet form into anything solid. And yet, within this seemingly uniform and featureless glow, there were whispers, ripples, infinitesimal variations in density, the gentlest of fluctuations, where some regions were ever so slightly denser, ever so slightly heavier than others. These weren't grand or dramatic variations. Imagine instead the surface of utterly still water at twilight. You might notice the faintest of undulations, barely visible, perhaps imperceptible to the casual glance, yet present. These density variations in the infant universe were measured in parts per 100,000. Nearly nothing, and yet nothing and everything, is the distance between a universe that remains perfectly smooth and featureless forever and a universe that will one day birth the structures we see around us today. Stars, galaxies, galaxy clusters reaching across incomprehensible voids. When you look at the cosmic microwave background, that ancient light released when the universe finally cooled enough to become transparent, about 13.8 billion years ago, you are essentially looking at a map of those primordial whispers frozen in time. Modern telescopes, particularly instruments like the Planck satellite and the earlier WMAP measurements, have mapped these minute temperature fluctuations across the entire observable sky with extraordinary precision. And what scientists discovered was extraordinary. The slightly warmer regions of that ancient light corresponded to slightly denser regions of matter, the slightly cooler regions to slightly less dense ones. A cosmic baby picture, if you will, showing not the clusters themselves, those would take eons to grow, but the seeds, the initial conditions, the blueprints. Picture it this way. Imagine the universe as clay in a potter's hands, but the potter is not conscious, not intentional, but purely the action of gravity itself. Those primordial density fluctuations were the slight asymmetries in the clay, the imperceptible lumpiness. Gravity's work was to magnify these tiny differences over cosmic time. Where there was slightly more mass, gravity pulled harder. Where gravity pulled harder, more mass accumulated. Where more mass accumulated, gravity's pull grew stronger still. It is a feedback loop so gentle, so patient, that you might imagine it almost as breathing, the universe exhaling and inhaling on a scale that stretches across billions of years. In those earliest moments after recombination, when electrons finally bound with protons to form neutral hydrogen, and light was finally freed to travel, the universe was perhaps 99.99% uniform. The variations were genuinely imperceptible to any observer at that time. Yet those fractional percentages of difference were the seeds of everything that would follow. The seed of the Virgo cluster, the seed of the Coma cluster, the seeds of the vast superclusters that form the largest structures in the visible cosmos. The seed, in fact, of the galaxy cluster that would one day contain our own Milky Way, beholden to its gentle gravitational influence, orbiting within it like a leaf caught in a slow, invisible current. What made these primordial fluctuations so consequential is that they provided something for gravity to work with. Gravity, you might say, abhors uniformity. It is an amplifier of differences. The universe needed those ripples, those asymmetries, to have anything to pull together. Without them, matter would have remained forever diffuse, forever uniform. No galaxies, no stars, no possibility of life wandering about its own origins on some distant world, orbiting a yellow star within a spiral galaxy. The very fact that you exist, listening to these words, traces back to those infinitesimal density variations imprinted on the face of the cosmos when it was younger than you are now, by a factor of incomprehensible magnitude. The early universe, then, was not sleeping, but it was in a deep state of potential, of quiet becoming. Those faint ripples in the cosmic microwave background were less like waking events and more like the first movements of a dreamer, the subtle shifts of one drifting slowly into a profound slumber, where the real work happens in the invisible realm. The structure we see today, the clusters, the voids, the vast filaments along which galaxies cluster like beads on a cosmic string, all of it emerged from those whispers. All of it grew out of the patient magnification of the almost nothing. The physicists and cosmologists who have studied these primordial fluctuations often speak of the elegance of what they find. The universe obeyed rules. The pattern of variations matched predictions from inflationary theory, the idea that in the first fraction of a second, the universe underwent an exponential expansion so rapid that it smoothed out irregularities, while simultaneously amplifying quantum fluctuations to cosmic scales. Those quantum fluctuations became the seeds. Inflation was the mechanism that transformed the infinitesimal into the inevitable. Yet this remains, to some degree, a tapestry woven from inference and elegant mathematics. We see the echo of inflation in the cosmic microwave background. We have not yet directly observed inflation itself. This is speculation, though educated, thoughtful speculation, grounded in decades of observation and theoretical work. What we know with greater certainty is that by about 100 million years after the Big Bang, those original density variations had grown. Gravity had been working in silence, gathering more and more matter into those initially imperceptible bulges. Dark matter, which we'll explore more gently soon, was accumulating invisibly, creating gravitational wells into which ordinary matter, the hydrogen and helium and trace amounts of heavier elements, was beginning to pour. The first stars were igniting. The first galaxies were beginning to take shape, and within regions where the original density fluctuation had been somewhat more pronounced, there were already hints of what would become the core regions of galaxy clusters, places where gravity was drawing in matter from an ever-widening sphere of influence. These protoclusters were not yet the grand structures we recognize today. They were not yet the home to hundreds or thousands of galaxies. They were embryonic, fragile perhaps, though gravity's patient hand was strengthening them with every passing million years. But the seed had been planted, back in that moment when the universe was 380,000 years old, and the cosmos was glowing with the warmth of its own origins. Everything that would follow, the grand cosmic architecture we observe today, the slow cosmic dances we are about to trace together, all of it began with those whispers. The faintest of asymmetries in a universe that was almost perfectly smooth. In those first few 100 million years after the universe's infancy, something remarkable began to unfold in the darkness. The faint density ripples encoded in that ancient light, those whispers of variation in the cosmic microwave background, started their slow transformation into something visible, something real. Gravity, patient and relentless, began its work, and the architect of this silent construction was something we cannot see, yet whose presence shaped everything that followed. Dark matter, invisible as it remains to this day, accumulated along those ancient density pathways, like water finding the subtle contours of a landscape in the darkness. Imagine vast filaments of this unseen substance, threading through the early universe, creating a skeletal framework, a cosmic scaffolding upon which all visible matter would soon gather. The dark matter did not clump randomly. It followed the geometry laid down by those primordial fluctuations, and as it accumulated, its gravity deepened, creating wells of gravitational potential into which ordinary matter, the gas clouds and incipient galaxies, would inevitably flow. The hydrogen and helium gas, still mostly ionized in the glowing early universe, began to be drawn toward these dark matter concentrations. This was not a violent collapse, though it might seem so in the language of physics. Rather, it was a gradual accumulation, a slow gathering of material toward cosmic neighborhoods that gravity had already marked as special. The gas cooled as the universe expanded and aged. It grew denser around these dark matter nodes, and within those densening regions, the first stars were forming, brilliant, short-lived giants that would blaze and fade in mere millions of years, their deaths seeding space with the first heavy elements. Do you notice how this process mirrors something we might recognize in quieter contexts? A gathering, not imposed from without, but arising naturally from the contours of space itself, from geometry, and the fundamental force that shapes everything. The young proto-galaxies, that is what these first agglomerations of stars and gas are sometimes called, began to emerge within the deepening potential wells of dark matter. They were not yet the sprawling, complex structures we see today. Many were smaller, more chaotic, still assembling themselves. And yet, even as individual proto-galaxies formed, they were not isolated. The dark matter scaffolding that nurtured each one also created pathways between them. Gravitational attraction between neighboring proto-galaxies, subtle and patient, began to draw them toward one another. This was the birth of structure, not individual galaxies floating in a void, but groups, clusters, interconnected webs of matter, all bound by gravity. The dark matter formed the invisible glue, present in far greater abundance than all the stars and gas combined, yet known only through its gravitational influence. Over hundreds of millions of years, these proto-clusters slowly assembled. The process was remarkably gentle by cosmic standards, a gradual inflow of matter along the dark matter filaments. There was no collision, no violent impact, only the steady, inevitable acceleration of matter following the curves of space-time itself. The gravity wells grew deeper as more mass accumulated. The dark matter infrastructure, formed in the earliest moments, remained relatively unchanged, like the bedrock beneath a landscape that guides water downhill. Picture, if you will, the universe at this epoch as a vast network of these gathering regions. In some places, the dark matter scaffolding was particularly robust, creating deeper wells. These would become the seeds of the most massive clusters we observe today. In other regions, the framework was more delicate, leading to smaller structures, what we now call galaxy groups, containing merely dozens of galaxies rather than thousands. But everywhere the principle was the same: dark matter setting the stage, ordinary matter flowing inward, and within that material, the first generations of stars lighting up. What is perhaps most soothing to contemplate is the inevitability of this process. Given the laws of physics and the initial conditions set down in that distant moment after the Big Bang, this outcome was not a surprise or a contingency. It was written, in a sense, into the geometry itself. The universe did not decide to form galaxy clusters through some accident or rare stroke of fortune. The mathematics that governed its expansion and the distribution of matter virtually guaranteed that such structures would emerge. Gravity, working with infinite patience, simply carried out what the universe's initial conditions had encoded. The dark matter, too, followed a kind of logic that is almost peaceful in its inevitability. It accumulated where the primordial density was slightly higher. It did not scatter or resist. It did not create turbulence or chaos. It simply responded to the gravitational gradient, gathering where gravity drew it, creating the deep wells into which galaxies and gas would pour. Over millions of years, layer by layer, filament by filament, the protoclusters assembled themselves into something that would, over billions of additional years, become the largest gravitationally bound structures in existence. And as you contemplate this slow assembly of the first protoclusters, consider that you are witnessing, through the lens of knowledge, something that required no intervention, no outside architect. The dark matter and the visible matter and the fundamental laws of gravity were sufficient. The universe, from its earliest moments, contained within itself the seeds and the mechanisms for its own elaboration. The protoclusters grew not through effort or will, but through the simple, patient operation of physics, as reliable and constant as the rhythm of breathing itself. And yet, as these proto-clusters gathered their first galaxies across those early millennia, something invisible was doing the real work, something that leaves no light, casts no shadow of its own, and yet holds the entire cosmic architecture together with a patient, invisible hand. This is dark matter. And to understand how we know it exists, we must follow a beam of light traveling across the universe for billions of years, only to be gently bent and curved by something it passes near. Imagine standing at the edge of a vast, still pond at twilight. The water is perfectly transparent. You cannot see it. And yet, when light from a distant star passes through it, the water bends that light ever so slightly. The star appears to shift a little, doesn't it? This is the principle that reveals dark matter's presence in galaxy clusters. It's called gravitational lensing, and it is, perhaps, one of the most elegant ways the universe whispers its secrets to us. In a galaxy cluster, there is so much mass concentrated in such an enormous region that the very fabric of space itself curves around it. This is not a metaphor. Einstein showed us that gravity is the bending of space-time itself. When light from a galaxy far behind a cluster travels toward us, it doesn't move in a straight line. Instead, it follows the curvature of space that the cluster's immense mass has created. The light bends. Sometimes it bends so much that a single distant galaxy appears as a smeared arc across the sky, a ghostly crescent of stretched starlight. Other times, the bending is so precise that we see multiple images of the same distant galaxy appearing in different places on the sky, each one traveling along a different curved path around the cluster. What makes this so profoundly revealing is this. When astronomers measure how much light bends as it passes through a cluster, they can calculate how much mass the cluster must contain. They add up all the light from all the galaxies visible within it, the billions of stars, the dust, the gas. And then they compare. The light, alone, accounts for only about 15% of the mass needed to bend the light by the observed amount. Where is the rest? The answer is invisible. It is dark matter. Dark matter is not like ordinary matter. It does not clump into stars or planets. It does not emit light or absorb it. It passes through ordinary matter almost without interaction, like a ghost walking through a wall. And yet it responds to gravity, and it exerts gravity upon everything around it. In a strange way, dark matter is more abundant than everything we can see. For every kilogram of ordinary matter in the universe, every atom that makes up you, the Earth, the Sun, every star you can see, there are roughly 5.5 kilograms of dark matter, invisible and patient, holding everything in place. The first hint that dark matter existed came from a Swiss astronomer named Fritz Zwicky in the 1930s, working in the mountains of California. He observed the Coma Cluster, a nearby gathering of thousands of galaxies, and measured how quickly they were moving within that cluster. He found something peculiar. They were moving far too quickly. If the cluster's mass was only the mass of its visible galaxies, those fast-moving galaxies should have flown apart long ago, scattered into the darkness of space like birds released from a cage, and yet they stayed, bound together. Zwicky had the intellectual courage to propose something radical. There must be far more mass in the cluster than we can see. He called it dark matter, and for decades, his colleagues considered the idea rather extraordinary. Yet Zwicky's vision was right. Now, when astronomers observe the warping of starlight in a distant cluster, they are seeing the presence of dark matter made visible through its effects. The light bends because space-time is curved, and space-time is curved because of mass, the great majority of which is dark. In this way, we have become accustomed to the strange paradox of modern cosmology. We can see the invisible more clearly than we can see the visible. The gravitational lensing itself is a phenomenon of profound beauty. When you look at images from space telescopes trained on clusters like Abell 1689, you see rings and arcs of light surrounding the cluster's center. These are distant galaxies whose light has been bent and magnified by the cluster's gravity well. Some arcs are thin and bright, so precisely curved that they seem almost unreal, like perfect brushstrokes painted by some cosmic artist. The light has traveled for billions of years to reach us, and in those final moments before arrival, the invisible dark matter has rearranged its path, sculpted it, made it visible. One might wonder, why do we trust this explanation? Why do we accept that dark matter is real when we cannot directly detect it? The answer is in the consistency of the method. Gravitational lensing is not the only way we know dark matter is there. When we observe the rotation curves of galaxies themselves, how quickly they spin at different distances from their centers, we find the same mystery. They spin far too quickly at their outer edges to be held together by visible matter alone. The motions of galaxies within clusters, the way they orbit and circle each other, the patterns we observe in the cosmic microwave background radiation, the large-scale structure of the universe itself, all of these independent observations point toward the same conclusion. Dark matter is woven throughout the cosmos. It is more fundamental than the matter we can see. It is the gravitational scaffold upon which all visible structure hangs. And so, as we continue our journey through these proto-clusters gathering in the early universe, understand that what we see, the brilliant galaxies, the young stars blazing into existence, is only the brightest thread in a much larger tapestry. The invisible dark matter is the loom itself. It is the patient architect, quietly assembling the frameworks into which ordinary matter falls, where it collects, where it coalesces into galaxies and stars, and someday, perhaps, into worlds where conscious beings might arise and eventually wonder about their own origins. And so the universe, in its patient arithmetic, began to write the story of how these clusters would form, billions of years unfurled in the darkness, and through it all, the invisible scaffolding of dark matter continued its silent work, guided by gravity's ancient choreography. The filaments that had been seeded in those primordial density ripples began to trace themselves across the cosmos, like threads being drawn through an incomprehensibly vast loom, each one aligned with the gravitational architecture that dark matter had established in the deepest past. Picture, if you will, the universe as it existed 3 billion years after the Big Bang. Matter was not scattered evenly through space. Instead, it collected into strands, into vast threads of concentrated dark matter and ordinary gas, forming what cosmologists now call the cosmic web. These filaments were not solid structures in any earthly sense, but rather concentrations of gravitational pull, regions where the density of matter, both visible and invisible, was just slightly greater than the mean. And yet that slight difference, when measured across billions of light-years, created an enormous asymmetry. Gravity, patient and relentless, could amplify these minute variations into the dominant architecture of the universe itself. Along these filaments, galaxies and galaxy clusters would preferentially gather. The filaments, you might imagine, acted like gentle funnels or channels through the cosmos. Gas and dark matter, drawn by the gravitational wells that formed along these threads, would flow toward nodes, toward intersections where the filaments met. At these nodes, the density grew higher and higher. The gravitational pull intensified. More and more galaxies found themselves caught in this ever-deepening well, drawn inward by forces they could not resist. Consider what this meant at a single growing cluster. Imagine a region of space, perhaps a few million light-years across, where dark matter was beginning to concentrate. Into this region, the filaments fed matter continuously. Billions upon billions of galaxies, most of them small and ancient, were guided along these cosmic highways toward the growing core. Some fell in rapidly, plunging through the outer reaches of the cluster in a matter of hundreds of millions of years. Others moved more slowly, in a kind of cosmic cascade, spiraling gradually inward as their orbital energy was dissipated by interactions with the surrounding environment. Over vast stretches of time, the cluster grew denser, more concentrated, more bound together by its own accumulating gravity. This process was not uniform. The universe, in its way, is a structure of varied intensities. Some filaments were thicker, richer with matter. Some nodes attracted more material than others. Where two or more major filaments intersected, the resulting cluster would be particularly massive, potentially harboring thousands of galaxies within its gravitational embrace. Other nodes, where the filaments were thinner or more distant, would gather fewer galaxies and remain somewhat less densely populated. And yet all of them, whether grand or modest, followed the same essential pattern. Matter flowed inward along the cosmic web. Gravity amplified the process. Clusters grew. By a few billion years ago, these structures had begun to stabilize somewhat, though they were never truly static. Within a cluster that had been growing for 5 or 6 billion years, the galaxy population had reached some kind of dynamic equilibrium. The core had become very dense indeed, with galaxies orbiting at velocities of thousands of kilometers per second, their speeds determined by the immense gravitational mass accumulated at the center. The outer regions remained somewhat more sparse, but still gravitationally bound, still slowly accreting additional matter from the surrounding filaments. Can you sense the patience in such a process, the slow inevitability of gravity at work across such scales? What made this process particularly subtle, and what made it so difficult for astronomers to understand for many decades, was that most of the matter doing the funneling, most of the scaffolding along which the galaxies flowed, was dark. The dark matter filaments could not be seen directly. They revealed themselves only through their gravitational effects, through the way the visible galaxies moved, through the clustering patterns that emerged. It was as though the universe had constructed the framework of its own architecture in invisible material, and then populated it with visible galaxies like gems placed along invisible threads. The time scale of this process deserves a moment of reflection. We are speaking of billions of years. A billion years is a span of time that exceeds the entire history of life on Earth by a factor of more than 2. Yet across 8 or 9 or 10 billion year stretches, the structure of clusters was gradually being assembled. A human observer, if one existed and could somehow remain conscious across such time, would perceive this process as almost infinitely slow. The motion of individual galaxies from one part of a filament to another might measure perhaps a few kilometers per second. At such velocities, over a single human lifetime, a galaxy would travel only a few hundred light years. Yet across a billion years, that same galaxy would journey hundreds of millions of light years, swept along by the currents of the cosmic web toward its ultimate resting place in the gravitational well of a massive cluster. The filaments themselves gradually thickened as matter accumulated. What had begun as an extremely slight overdensity in the distribution of dark matter, perhaps only 0.1% denser than the cosmic average, became increasingly pronounced. A filament that at early times might have been detectable only through careful analysis of the clustering patterns of galaxies became, over billions of years, a visibly dense structure in modern surveys, a clear thread of enhanced matter density stretching across space. And at the nodes, at the intersections where multiple filaments converged, the densities became extraordinary. These nodes would eventually host some of the most massive and impressive structures in the observable universe, clusters containing trillions upon trillions of stars distributed among thousands upon thousands of galaxies. Reflect for a moment on what this reveals about time itself, about the relationship between time and structure in the universe. Without billions of years, without the vast span of cosmic history, such structures could not exist. They are monuments to duration, to the slow accumulation of gravitational effects across unimaginable distances, and yet they reveal themselves as entirely natural, entirely inevitable given the initial conditions, the primordial density fluctuations, and the fundamental laws of gravity. Is there not something deeply restful in this recognition, in understanding that the complexity and grandeur of galaxy clusters arose not through violence or sudden catastrophe, but through the patient, methodical action of gravity over billions of years? Between these galaxies, in the spaces we once thought were empty, something vast and invisible dwells. It is not the darkness of vacuum, but rather a presence so immense, so thoroughly distributed through the cluster, that for decades it remained entirely undetected by human instruments. Yet it is there, filling the space between galaxies with a warmth that would astonish us if we could ever feel it directly. Picture, if you will, the interior of a galaxy cluster not as a sparse scattering of stars and dust, but as something closer to an ocean, vast, continuous, permeating everything. This is the intracluster medium, a vast reservoir of gas heated to tens of millions of degrees. The temperature within these regions often reaches 50 million, sometimes 100 million degrees Kelvin, and yet, paradoxically, this inferno goes unseen by our eyes. It does not shine with visible light. It whispers to us only in X-rays, those penetrating waves that pass through ordinary matter as though it were transparent. When astronomers first turned sensitive X-ray telescopes toward galaxy clusters in the latter half of the 20th century, they encountered something unexpected. Around and between the galaxies themselves, a faint but unmistakable glow emerged from the detector. That glow was the signature of this superheated gas, radiating its energy across billions of light-years of space. The gas we see today in these X-ray images began its heating journey billions of years ago, gradually accumulating within the cluster's gravitational grip, growing warmer as it fell inward, compressed by the relentless pull of all that gathered mass. What maintains this extraordinary temperature? Gravity itself. As the universe's largest structures form, material falls inward along the cosmic web's invisible filaments. This infall generates tremendous kinetic energy. When particles collide at such velocities, their motion converts into heat. And once confined within a cluster's gravitational embrace, this heat has nowhere to escape. It remains trapped, radiating slowly into space across the ages, yet never dissipating fast enough to cool substantially. The intracluster medium is, in essence, the heat signature of cosmic structure itself, written in X-rays against the darkness. The composition of this gas is predominantly hydrogen and helium, the most abundant elements in the universe, mixed with small traces of heavier elements forged in the hearts of stars and scattered outward through billions of years of stellar death and recycling. This mix gives the intracluster medium a certain continuity with the galaxies it surrounds. The same elements that formed stars within those galaxies also float freely in the space between them, part of an interconnected whole. Can you imagine that relationship? Galaxies not as isolated islands, but as expressions of a single, unified structure. The density of this gas is extraordinarily low by any terrestrial standard. In the densest clusters, the intracluster medium might contain perhaps 1 particle per cubic centimeter. In our everyday experience, the air we breathe contains roughly a billion particles in the same volume. Yet despite this delicate thinness, the sheer volume involved, spanning millions upon millions of light-years, means the intracluster medium actually outweighs all the galaxies within the cluster combined. It is a hidden ocean vastly more massive than all the visible stars and planets and gas clouds that form the luminous structures we can see. The distribution of this gas is not uniform. It tends to concentrate more densely toward the cluster's center, where the gravitational pull proves strongest. The density gradually decreases with distance from that gravitational heart, fading softly into the thinner intergalactic medium that surrounds the cluster. This gentle gradient, this slow transition from density to emptiness, creates a kind of atmosphere around each cluster, an invisible envelope that distinguishes the inside of a cluster from the vast spaces beyond it. There is a quietness to contemplating this ocean of unseen heat. For billions of years, this gas has floated silently within these structures, radiating its energy into the void, asking nothing of us, making no sound that our ears could ever perceive. It moves in great currents and flows, influenced by the motions of the galaxies that swim within it, and by the invisible scaffolding of dark matter that guides everything. Sometimes these currents swirl and eddy around particularly massive galaxies, creating patterns of hot and cool gas that X-ray telescopes eventually learn to discern. The intracluster medium also serves as a kind of historical record, a repository of information about the cluster's past. The temperature variations within the gas reflect the energy released by past events, mergers of smaller clusters, infalls of matter, the gravitational interactions of galaxies. By studying the subtle patterns in X-ray emissions, astronomers can read the history of cosmic violence and congregation written in the heat distribution. What might we infer from those patterns about the cluster's ancient past? Perhaps stories of slow collisions, quiet accumulations, the patient gathering of structures across time. And yet, despite its vastness, despite its overwhelming mass, this medium remains fundamentally invisible to most forms of observation. A visible light telescope pointed at a galaxy cluster would show only the galaxies themselves, perhaps the thin traces of dust. The intracluster medium would vanish entirely from view. It is a humbling reminder that the universe's most dominant structures are not always the ones we see most easily. There is a profound peace in that knowledge, that reality extends far beyond the narrow band of perception we call visible light, that our universe is vastly richer and stranger than any single view could capture. The warmth of the intracluster medium persists across the eons, radiating gently outward, carrying away the energy of cosmic structure formation in a slow, patient release that will continue for untold ages yet to come. As the universe unfolds across billions of years, and filaments pull and guide great rivers of matter toward gathering points of unimaginable density, there exists a structure so near to us, so intimately woven into the slow gravitational dance of our own cosmic neighborhood, that we might think of it as a kind of anchor, a quiet center around which our own galaxy and all the star islands bound to us gently orbits. This is the Virgo cluster. The Virgo cluster lies some 50 to 60 million light-years distant from the Milky Way, which in cosmic terms means it dwells in what we might call our galactic backyard. It is not the largest cluster in the observable universe. That distinction belongs to other, more distant, more massive congregations. But the Virgo cluster holds something far more immediate and peculiar for us. It is the gravitational heart of the structure to which we belong, to which our local group of galaxies bows, ever so gently, across the vast and silent expanse between the stars. The local group itself, the collection of perhaps 80 galaxies, including our own Milky Way and the great spiral of Andromeda, moves through space with what we might call a slow, inevitable drift toward the Virgo cluster's center. This motion is not dramatic or sudden. It unfolds across scales of time so immense that 1 billion years passes like a single, drawn-out breath. And yet the pull persists, patient and unrelenting, a reminder that even in the vast darkness, even separated by millions of light-years, gravity's whisper reaches across the void and gently tugs. Within the Virgo cluster itself dwell somewhere between 1,000 and 2,000 individual galaxies, though the true number remains softly uncertain, shifting with each deeper observation. The cluster shimmers with a remarkable diversity of galaxy types, elliptical giants, their stars arranged in serene, rounded swarms, spirals like our own Milky Way, rotating with patient majesty, smaller, irregular forms, their shapes subtly bent and warped by the gentle collisions and gravitational interactions of their neighbors. To move through the Virgo cluster, if one could somehow traverse these cosmic distances, would be to witness a kind of tranquil abundance of light and structure. At the cluster's center, or near what we perceive as its heart, sits M87, a giant elliptical galaxy so massive and old that it represents, in many ways, the accumulated history of countless mergers and slow coalescences. M87 glows with the patient warmth of trillions of stars, many of them ancient, many of them in the final, quiet chapters of their stellar lives. Around M87's core there swirls, we now understand, one of the universe's most profound objects, a black hole of such tremendous mass that entire stellar populations could fall into its embrace. And yet it too is patient, it too is calm, it feeds on the slow trickle of matter that drifts toward it, and in this steady, quiet consumption, it releases jets of radiation that shine across millions of light years. What makes the Virgo cluster so significant to our own small corner of existence is the way it has shaped us. The local group's motion toward Virgo is not a recent development. It has been occurring throughout the entire history of our Milky Way, throughout the eons in which our galaxy has grown and evolved and developed its vast spiral structure. In a way, Virgo's gravity has been our compass, our lodestone, drawing us along a path through the cosmic web that was determined billions of years ago when the matter that would form the local group first began to clump together in the presence of the cluster's tremendous mass. The Virgo cluster also serves as a kind of threshold in our mapping of the universe. For much of the 20th century, astronomers thought of it as a defining boundary of the local universe, the great mass concentration toward which all nearby galaxies seemed to stream. It was not until more recently that a deeper understanding emerged. Virgo itself is merely a local concentration within an even larger superstructure, a swelling in the cosmic web that stretches across hundreds of millions of light years. And yet, despite this revelation, Virgo has not diminished in our understanding. If anything, it has gained a quieter significance. It remains, for us, a kind of gentle attractor, a structure through which we move, toward which we are pulled, and by which our neighborhood of the cosmos has been subtly shaped. The intracluster medium that fills the spaces between the galaxies of Virgo shimmers, like the rest, with that vast ocean of hot gas we discussed before. This gas has been heated by the cluster's own gravity and by the cascading energy released through galactic collisions and mergers. It glows in X-rays, invisible to our eyes, yet present in every cubic light-year of the cluster's volume. And the Virgo cluster's medium is perhaps one of the richest, most complex such environments yet observed, a vast, warm ocean in which thousands of galaxies drift and occasionally embrace, their motions choreographed not by will or intention, but by the patient mathematics of gravity. There is something almost maternal in the way one might imagine the Virgo cluster's influence on the local group. For millions of years, the cluster has been slowly drawing us inward, not violently, not suddenly, but with the gentle, inevitable persistence of gravity. Our galaxies, in turn, have remained bound to one another through their own lesser gravitational attractions. And as we drift together toward the center of that great mass, we carry within us our own stories, our own vast populations of stars and planets, and the slow unfolding of cosmic processes that have been occurring within our own island universes since they were born from the ripples in the early cosmos. Can we say that the Virgo cluster has shaped not only our motion through space, but also something deeper about who we are? Perhaps not in any direct sense. And yet the universe is a web of connections and influences, most of them subtle, most of them operating across timescales so immense that any single galaxy, any single star, seems almost infinitesimal in comparison. The Virgo cluster's gravity has influenced the density of the matter around us. It has influenced the rate at which our local group's galaxies approach one another. It has, in a quiet but undeniable way, shaped the context in which the Milky Way has existed and evolved. In the early 1933, a Swiss astronomer named Fritz Zwicky was studying a particular gathering of galaxies that we now call the Coma Cluster, and in his quiet observations lay a mystery that would reshape how we understand the invisible universe itself. The Coma Cluster sits roughly 300 million light-years away, in the direction of the constellation Coma Berenices, and contains thousands upon thousands of galaxies all moving together in what appeared to be a gravitational embrace. Zwicky was measuring the individual speeds of these galaxies, watching how they drifted relative to one another, trying to understand the nature of the gravity holding them together. And here is where something profoundly strange emerged from his calculations, something that whispered of a hidden presence in the cosmos. When you add up all the light from every visible galaxy in the Coma Cluster, every star, every glowing spiral and elliptical form that we can see through our telescopes, the total mass should have a particular gravitational strength. It should pull on the galaxies with a certain force. But Zwicky's measurements told a different story. The galaxies were moving far too quickly for the amount of visible matter that was present. They should have flown apart long ago, scattered like leaves in a wind, yet they remained bound together, moving at velocities that demanded the presence of gravity far stronger than visible light could account for. The mathematics were unambiguous. Something invisible, something massive, something utterly dark and unreactive to light must be present in and around the Coma Cluster in extraordinary abundance. Zwicky had stumbled upon the gravitational signature of dark matter, though he did not yet call it by that name. He called it missing mass, or sometimes Dunkel Materie, speaking in his native German. The term dark matter, in the sense we now use it, would take time to settle into the language of science. But the observation itself, the quiet recognition that the universe harbored vast amounts of matter beyond what our eyes and instruments could see, this was revolutionary. It suggested that everything we could perceive with light, every star and galaxy and nebula and glowing cloud, represented only a small fraction of what actually exists. What makes the Coma Cluster such a restful historical touchstone is that Zwicky's discovery was not immediately accepted. The scientific community moved slowly, methodically, skeptical as good science should be. For decades after his first calculations, the idea of missing mass remained more curiosity than consensus, a mathematical puzzle that most astronomers preferred to set aside. There was comfort in this slowness, actually, in the patient way that truth revealed itself across generations rather than in sudden fanfare. It was only much later, as technology improved and other observations accumulated, that the invisible scaffold of dark matter began to feel inevitable, woven into our understanding of how galaxies form and persist. The Coma Cluster became a kind of cosmic laboratory where the invisible became undeniable. Other astronomers studied it. Other measurements were taken. The cluster's unusually high velocity dispersion, the way its member galaxies moved with such speed through space, became a textbook example of how we infer the presence of things we cannot see. Every calculation reinforced the same conclusion, layer upon layer, until dark matter was no longer a curiosity, but a foundation upon which all modern cosmology rests. And yet, if you were to look at the Coma Cluster today through a telescope, you would see mostly what Zwicky saw, a beautiful, quiet gathering of thousands of galaxies, elliptical and spiral forms, some giant ellipticals dominating the core, smaller galaxies scattered throughout, all in that profound silence of space. The dark matter that holds it all together remains invisible, undetectable by any direct means we possess. It does not emit light. It does not absorb light. It simply exists, present beyond perception, felt only through the gentle but inexorable pull of its gravity. The Coma Cluster contains perhaps as much as 7 times more dark matter than visible matter, and yet you cannot see a single photon of it. It is as though the universe has kept its greatest secret tucked invisibly within the structures we do perceive. The historical significance of Zwicky's work with the Coma Cluster lies not only in the discovery itself, but in what it taught us about the limits of our perception. It showed us that the universe could hide an entire ocean of matter beneath what we thought was the surface of things. It demonstrated that gravity, that patient force which holds galaxies and clusters together, reaches far beyond the visible, touching invisible presences that we can only understand through mathematics and the language of motion. The Coma Cluster became a window into a vast, patient cosmos where most of what exists remains forever hidden from our sight, bound together in the darkness, turning slowly through the ages. Within these vast gatherings of galaxies, something unfolds that might seem violent from a human perspective, but which, when viewed across the true scale of cosmic time, reveals itself as something far more like an ancient ballet, slow, deliberate, and utterly silent. When 2 galaxies drift toward one another through the gravitational embrace of their shared cluster, they do not collide in any sudden way. Instead, they begin a dance that may take hundreds of millions of years to complete, their paths gradually converging as the infinite geometry of space-time gently curves them together. Imagine 2 swimmers in a vast, still pool, drawn imperceptibly toward each other by the gentlest current, moving so slowly that neither would notice the motion within a single human lifetime. Yet over the course of ages, measured in the millions of years, they drift inexorably closer. The first contact between such galaxies is tentative. Long tendrils of stars reach out from one galaxy toward the other, stretched by the uneven pull of gravity, what astronomers call tidal forces. These are not violent rips or tears, but rather the slow elongation of stellar streams, delicate ribbons of stars that unfurl across the darkness like silk scarves unwinding in an imperceptible wind. The outer regions of each galaxy begin to distort, their spiral arms, if they possess them, slowly stretching and warping. Sometimes these early stages create the most extraordinary structures, beautiful and transient asymmetries that persist for millions of years before merging becomes complete. Observers in distant galaxies, looking at the cluster through powerful instruments, would see these interim forms as strange, lopsided galaxies with tails and bridges of stars connecting them. It is a form of beauty that exists nowhere else in the universe except in these transitional moments of galactic encounter. As the merger progresses deeper into its long embrace, the cores of the 2 galaxies begin their eventual union. But still, this is not an instantaneous event. The passage through the cluster's thickening regions of hot gas and dark matter continues to slow their relative motion, drawing them in with what feels like patience itself. Individual stars within the galaxies rarely collide with one another. Space, even within a galaxy, contains such staggering emptiness that the probability of 2 stars meeting is vanishingly small. Instead, the galaxies pass through one another, their stellar populations mingling in ways that gradually become permanent. Stars from the first galaxy find themselves bound into the gravitational field of the second. The gas clouds that fill the galaxies, however, do interact more directly. These regions of hydrogen and helium, spread throughout both systems, collide and compress one another as the 2 galaxies merge, creating shock waves of invisible warmth that ripple outward. These compressions often trigger the formation of new stars, brief, brilliant moments of starbirth that punctuate the otherwise gradual unfolding of the merger. Consider what happens within the time frame of such an event. A galaxy merger viewed across mere thousands of years appears almost frozen, unchanging. Viewed across 1,000,000 years, subtle motions become apparent, the slow twist and stretch of galactic arms. Viewed across 10 million years or more, the transformation becomes undeniable, dramatic even, and yet to the universe itself, even these timescales are brief interludes. A cluster might contain dozens or hundreds of such mergers unfolding simultaneously in different regions, each one proceeding at its own rhythm, some beginning their gravitational descent, while others are completing their final coalescence into unified forms. The gravitational dynamics of a cluster make these mergers inevitable, and in a sense, beautiful. Each galaxy that falls into a cluster is destined eventually to merge with others, its trajectory shaped by invisible threads of gravity, stretching back to the earliest moments when the cluster itself was beginning to form. What might appear to be chaos, thousands of galaxies moving in countless directions, is actually the expression of deep order. The cluster is a system in slow equilibrium, its members bound by gravity into patterns that repeat themselves across billions of years. Mergers are not aberrations within this order. They are the mechanism through which that order sustains and evolves itself. As galaxies merge, they shed energy, lose momentum in a subtle way, and settle ever lower into the cluster's gravitational well. Over eons, this process causes the cluster itself to evolve, to become ever more tightly bound, ever more stable in its structure. The most remarkable aspect of these cosmic collisions is how little we see them as drama. There is no sound, no explosion visible to the eye, no sudden catastrophe. What occurs is a transformation so gradual and so vast in scale that it transcends our usual categories of violent and peaceful. It simply is a reordering of matter and energy across distances so great and timescales so extended that the entire process carries a quality almost like meditation. Galaxies that inhabited the cluster as separate entities thousands of generations in the future will exist as merged systems, their histories woven together into shared structures. And somewhere else in the cluster, new galaxies will be beginning their own slow approach towards similar fates. At the very heart of nearly every galaxy cluster sits something almost impossible in its scale, a single galaxy so vast, so luminous, so utterly dominant, that it seems to have consumed the architectural center of the entire cluster itself. These are the brightest cluster galaxies, or BCGs as astronomers call them in their shorthand, and they represent perhaps one of the most profound examples of cosmic patience. They are not born fully formed, rather, they grow in a process of almost meditative accumulation, becoming gently larger across billions of years, fed by the slow collisions and mergers of their smaller neighbors around them. Imagine for a moment the very heart of a cluster. The region is densest there. Matter has pooled, and gravity has drawn everything inward with inexorable gentleness. When one galaxy drifts too close to another in these crowded central regions, the encounter is not quick. It unfolds across millions of years, a slow waltz of two vast stellar systems drawn together by mutual gravity, their stars almost never actually touching, but their outer edges beginning to shred and stretch and mix. The smaller galaxy loses speed, spirals inward, and eventually merges with its companion. And in this merger, something essential happens. Material flows to the center, adding bulk and mass to whatever dwells there. With each encounter, with each addition, the central galaxy grows. Over the course of cosmic time, a pattern emerges at the cluster's heart. That central galaxy does not simply remain a single structure. It grows heavier, it grows larger. Its envelope of stars expands like warm dough rising in the slow heat of an oven. And because it is at the gravitational center of the cluster, it naturally draws more material toward itself than any other galaxy in the region. It becomes a collector, almost a cosmic sink, drawing in not just whole galaxies, but streams of smaller companions, orbiting collections of stars, even solitary wanderers that have drifted too near. Each addition is gentle, gradual, separated by tens or hundreds of millions of years, yet inexorable. The result is something almost beyond comprehension in its size. The brightest cluster galaxies are elliptical in shape, their structure bloated and diffuse, stretching across millions of light-years. Some are so large that our own Milky Way, which we think of as immense, would fit inside them like a marble rolling through a cathedral. They can contain as many stars as 1,000 Milky Ways, or more. They are among the largest single objects in the universe, structures so vast that light from one end takes hundreds of thousands of years to reach the other. What makes their growth particularly remarkable is its smoothness. Unlike the violent imagery we often attach to cosmic collisions, the process by which a BCG grows is fundamentally quiet. When a smaller galaxy merges with the central giant, its stars do not crash and explode. Instead, they are gently absorbed into the older, larger system. They orbit within it, their paths adjusted by gravity, their speeds equilibrating over time. The entire merger happens in silence, with no light, no sound, no disturbance beyond the slow rearrangement of matter itself. These galaxies are almost always old, predominantly composed of ancient stars, red and orange dwarfs that have been burning for billions of years. Their light is soft, a warm amber glow when viewed in deep images from space telescopes. It is as though they carry within themselves the accumulated memory of every collision, every merger, every gentle addition that built them to their current grandeur. Their color speaks of age, of stability, of a system that has settled into a kind of cosmic equilibrium at the cluster's core. The surfaces of brightest cluster galaxies fade gradually into their surroundings, their outer edges dissolving into the hot, glowing intracluster medium that fills the space between galaxies. In some ways, it becomes difficult to say exactly where the galaxy ends and the cluster begins. The boundary is not sharp but gradational, a slow transition from the denser regions at the center to the more diffuse material beyond. This gradual fading is itself a signature of the merger history, each ancient addition leaving a faint trace, a subtle asymmetry, a gentle ghostly shell in the stellar distribution that astronomers can sometimes detect when they examine the light carefully. Do you notice how, in a sense, the brightest cluster galaxy is a kind of cosmic record? Its very structure encodes the history of collisions it has survived. Within its envelope of ancient stars are encoded billions of years of quiet growth. This is why astronomers study them, not for the violence implied by the word merger, but for the story they tell about how structure slowly consolidates in the universe, how gravity patiently orchestrates complexity from simplicity across the depths of time. Some of these central galaxies grow so enormous that they develop a peculiar feature called a CD halo, a vast, extended envelope of even fainter material that can stretch outward for tens of millions of light-years. The CD stands for supergiant D, a classification from the old morphological schemes, but what matters is that this outer halo represents the cumulative debris, the extended skirts, of all the countless mergers that built the galaxy beneath it. It is almost ghostly in its dimness, barely visible against the darkness of space, yet it speaks of an unimaginably long history of quiet accumulation. The presence of a brightest cluster galaxy also serves a subtle gravitational function. At the very heart of each cluster, gravity is strongest, and the presence of such an immense central object acts as a kind of anchor for the entire system. The galaxy helps stabilize the cluster's core, its gravity ensuring that the densest region remains bound, that the intracluster medium remains gathered. In a sense, the brightest cluster galaxy is both a product of the cluster's evolution and a stabilizing force for its continued existence. It is at once an effect and a cause, a passive accumulation that becomes an active participant in shaping the structure around it. There is something deeply restful about contemplating these structures, if one allows the mind to rest in the contemplation. Here is no conflict, no emergency, no need for urgency. Here is only the patient, inevitable work of gravity, the slow gathering of matter, the quiet growth of objects across cosmic ages. 1 billion years passes, and a BCG grows slightly larger. Another billion years, and it grows again. Time moves differently at this scale, in this context. The mergers that would seem cataclysmic if they happened to stars, the collision of entire galaxies, each containing billions of suns, become merely gentle events in the long narrative of the cluster's existence. They are the cosmic equivalent of sinking deeper into sleep, of one thought blending into another, of time becoming less distinct, less urgent, less sharp. Each merger is a kind of softening, a blending together, an addition that makes the whole slightly larger and slightly softer and slightly less distinct from the space around it. Within these sprawling cosmic gardens of colliding galaxies and invisible dark matter, something remarkable occurs that seems almost like an act of celestial artistry. Light itself becomes a canvas. When photons from the most distant galaxies travel toward us, across billions of light years, they pass through the immense gravitational fields of massive galaxy clusters that lie in their path. And when light moves through such a warped landscape of space and time, something extraordinary happens. It bends, it curves, it stretches into shapes that have fascinated astronomers for decades now, shapes that seem too perfect, too haunting to be real. These are gravitational lenses, and they offer us perhaps one of the most graceful proofs of Einstein's profound insight about gravity itself. Consider Abell 1:1689, a galaxy cluster so densely packed, so thoroughly woven with dark matter, that it bends space around itself like the surface of a troubled pond. This cluster lies roughly 2 billion light-years away, and it contains not just thousands of galaxies, but dark matter equivalent to perhaps 100 trillion suns. When the light of even more distant galaxies that lie beyond this cluster, in the deeper reaches of space, passes through Abell 1689's gravitational well, the light doesn't travel in a straight line. How could it? Space itself is curved there. The light bends, sometimes splitting into multiple images of the same distant object. Sometimes it stretches into elegant arcs, long thin curves that ring the cluster like ghostly halos. Astronomers call these features Einstein rings when they form perfect circles, or more commonly, gravitational arcs when they trace partial curves through the darkness. What makes this so extraordinary is not just that the bending happens, but that we can see it at all. In the absence of such lensing effects, those ultra-distant galaxies would be far too faint for our instruments to detect. Their light is simply too spread out across the void. But the gravity of the cluster acts like a cosmic magnifying glass, bending the light rays and bringing them into focus. It concentrates light that would otherwise have scattered beyond our reach. The distant galaxy becomes visible, multiplied, magnified, distorted perhaps, but visible nonetheless. It is as though the universe itself has arranged for us to see deeper into time and distance than we otherwise could, if only we understand how to read these light-bent messages written in warped geometry. The colors and patterns of these lensed arcs hold profound truths. Each arc we observe in an image like Abell 1689 reveals not just the position and brightness of a distant galaxy, but something far more intimate, It tells us about the distribution of dark matter in the foreground cluster. By carefully mapping where these arcs curve, how much they're magnified, how they split and multiply, astronomers can reconstruct the invisible dark matter scaffold of the cluster itself. It's a gentle interrogation of the cosmos, carried out in light and shadow. The cluster becomes a tool. Its gravity becomes a window into its own hidden nature. There is something deeply meditative about this. The idea that what obscures also reveals, that what bends our view also offers us clarity. Imagine the patient work required to witness this. Astronomers spend nights at telescopes, collecting photons that have journeyed for billions of years. They measure the precise positions of these glowing arcs with exquisite care. They model the gravity, run simulations, refine their understanding of where the dark matter must be. Each observation is like a brushstroke in an ancient, slow-forming portrait. The clusters themselves paint with time and gravity. We simply read what they have painted across the fabric of the universe. There is a tranquility in how these lenses work, a kind of ancient patience. The light began its journey when the universe was much younger than it is now. It traveled through cosmic time, past clusters and galaxies, through the thin medium between stars. And then, at precisely the right moment, it encountered this region of warped space. The cluster's gravity caught it, curved it, brought it into focus. The light that arrives at our telescopes carries within it the memory of every field it passed through, every curve it navigated. We look at Abell 1689 and see not just one moment, but echoes of the universe's shape written in luminous arcs. Other clusters perform similar miracles. Abell 370, another dense knot of galaxies, creates its own constellation of lensed arcs, some of them forming not simple curves but complex, interwoven patterns that seem to tell stories of hidden galaxies beyond. The Bullet cluster, born from the collision of two massive clusters, creates lensing patterns so distinct that they revealed the separation of dark matter from ordinary matter during the merger itself, a confirmation of dark matter's reality through one of the most direct visual means we possess. Each cluster is a different lens, each offering a different view of what lies beyond and what lies within. The mathematics underlying all of this is beautiful in its elegance, but it is also deeply calm. The equations of general relativity that describe how mass curves spacetime are not complicated in their essence. They are flowing, inevitable, like water finding its path. Einstein understood that gravity is not a force pulling matter together. It is the curvature of space itself, caused by the presence of mass and energy. A cluster sits in space like a weight on a stretched rubber sheet, and the sheet curves smoothly around it. Light follows the contours of that curvature. There is no force, there is only geometry, pure and simple. What draws us to contemplate these cosmic lenses, perhaps, is their reminder that the universe operates according to principles we can understand. The light bends according to laws. The dark matter arranges itself according to those same laws. We are not isolated observers in an incomprehensible cosmos. We are readers of a text written in mathematics and light. The clusters, the lenses, the distant glowing galaxies, they all speak to us in a language we can learn to understand. Slowly, patiently, over decades of observation and refinement, we are learning to hear what they say, and in learning, we find ourselves drawn deeper into the slow, meditative contemplation of how the universe is woven together, gravity binding light and matter and time into patterns of astonishing grace. And yet, within this cosmic dance of clusters, these islands of gravity scattered across billions of light years, there exists a layer of organization so vast that even galaxy clusters themselves appear as mere threads in a greater tapestry. We stand now at the threshold of understanding the largest structures the universe has arranged, and the place where our own galaxy finds itself cradled within unimaginable scales of order. Beyond the clusters themselves lies the concept of superclusters, those filamentary arrangements where dozens or even hundreds of galaxy clusters gather along the invisible scaffolding of dark matter, bound together by gravitational embrace, so gentle and so slow that the motion takes billions of years to unfold. These superclusters are not compact like their constituent clusters. Rather, they stretch across hundreds of millions of light-years as elongated strands, as vast cosmic filaments through which matter flows in the slowest of currents. Picture, if you will, the difference between a tightly woven thread and the gossamer strands of a spider's web catching the morning light. Superclusters are the latter, delicate and extended, holding their form through gravity's patient pull rather than through any density of concentrated mass. Our own Milky Way does not float alone in the vast darkness. It belongs to a structure named Laniakea, a name drawn from Hawaiian, meaning the immeasurable heaven. This supercluster contains not only our galaxy and the Andromeda Galaxy and all the dwarf galaxies that attend them in the local group, but it encompasses the Virgo cluster that exerts its subtle gravitational influence upon us, and the Fornax cluster beyond, and thousands upon thousands of other galaxies arranged across a region of space so enormous that light itself requires 150 million light-years to traverse its breadth. When astronomers finally mapped Laniakea in detail only a decade ago, it became clear that what had once seemed like the simplest architecture of the cosmos, our local group flying outward through an otherwise featureless void, was in fact part of a graceful, flowing structure, a cosmic current within which our galaxy drifts. Within Laniakea, there exists a subtle gravity gradient. The supercluster possesses a center, a region of slightly greater density, toward which all its constituent galaxies and clusters experience a gentle acceleration. This center is not a place of violent convergence or dense accumulation. Rather, it is a quiet pooling, a direction toward which everything slowly rolls, as if the fabric of space itself held the slightest of slopes. Our Milky Way, along with all the other galaxies of the local group, finds itself drawn toward this center with accelerations measured in kilometers per second, a motion so gradual that were you to ride upon a galaxy, you would perceive no sensation whatsoever, only a slow and patient shift in the distribution of matter around you across epochs of time. The discovery that superclusters possess these coherent flows, rather than serving as static, unchanging grids of structure, revealed something profound about the universe's organization. Instead, it is a fluid medium in which great rivers of galaxies flow along the valleys of matter, following the contours of dark matter scaffolding laid down in the universe's first moments. These flows are not rapid or chaotic. They are measured in the patient cadences of billions of years. Yet they are persistent, inexorable, shaping the very geography of the observable universe. And within this framework, one may ask, what significance holds a single galaxy, or even a single cluster, against such immensity? The question itself carries a restful quality, does it not? The recognition that our own place in the cosmos is nested within nested structures, each larger and more patient than the last. We exist within the Milky Way, which exists within the local group, which exists within the gravitational embrace of the Virgo cluster, which forms part of the Laniakea supercluster, which itself is but one thread among countless others in the cosmic web. Each structure contains the next, each one larger, each one taking longer to form and longer still to change. The mapping of Laniakea has suggested to cosmologists that our supercluster may itself be in motion relative to other superclusters, that there may exist even grander flows of matter through the universe, currents so vast and so slow that they unfold across timescales that dwarf the age of stars themselves. In the peaceful contemplation of this possibility lies a peculiar comfort. The universe is not a place of solitary isolation, but of belonging to structures of increasing vastness and increasingly patient motion. We are held, cradled, moved along by forces that operate on timescales that render human anxiety meaningless and urgent concerns weightless. Within Laniakea, galaxy clusters slowly orbit their common gravitational center. Galaxies within those clusters slowly orbit the cluster's heart. Our own Milky Way traces its own path, influenced by all these currents at once, yet stable in its own rotation, providing shelter for its hundreds of billions of stars. The nested quality of these structures, the way each contains and nests within the other, creates a sense of profound order, an organization that speaks to something deep within the resting mind, the recognition that complexity can be serene, that vastness need not inspire dread, but rather a kind of peaceful surrender to forces far greater and far more patient than ourselves. Picture the universe not as it is now, but as it will be in the almost unimaginably distant future. In perhaps 100 billion years, or 1 trillion, the clusters we have been following will find themselves in a state that is fundamentally different from the one they exist in now. The cosmic expansion that has always been gently pulling the universe apart will have grown more powerful, more relentless, and the effect will be felt most acutely by the structures on the largest scales. The superclusters, those vast assemblies of clusters held together by their own gravity, will continue to move apart. The Laniakea supercluster, that colossal structure we spoke of earlier, which contains our own cluster within it, will drift further and further from its neighboring superclusters until the light from those distant structures can no longer reach us. One by one, the distant superclusters will slip beyond the edge of the observable universe, as seen from our vantage point, pulled away by a cosmic expansion that accelerates with each passing age. But what of the clusters themselves, the closer gravitationally bound structures? Here, the picture becomes quieter still, and perhaps more melancholy in its way, though it is spoken of with perfect scientific calm. Within a few 100 billion years, the local group, that modest collection of galaxies to which we belong, gently anchored by the gravitational pull of Andromeda and our own Milky Way, will have merged into a single elliptical galaxy. The Virgo cluster, which once drew our local ensemble toward it with its enormous gravitational presence, will itself have grown darker as its own expansion continues and the less tightly bound clusters and groups around it drift away. Think of it this way: the universe will become increasingly lonely, one structure at a time. The clusters that are bound together by gravity will remain together. The Coma cluster will persist, its thousands of galaxies still orbiting their common center of gravity, still stirred by the invisible dark matter that first drew them together so long ago. But around them, the voids will become even more profound. The other clusters that once inhabited the same cosmic neighborhood will have disappeared beyond the horizon, carried away by expansion into regions of space no longer connected to us by any light, any signal, any force that matters at human or even cosmic scales. In this far future epoch, the universe will have a strange character. It will not be empty. Galaxies will still burn, still evolve, still undergo subtle changes as their stars age and perish. But the view from any given cluster will be one of profound solitude. The distant light we can see today, the ancient glow of countless galaxies stretching back toward the edge of the observable universe, will have receded beyond sight. What an observer in that distant age might see, if there are observers at all, would be a universe seemingly confined to their own cluster, surrounded by absolute darkness and infinite emptiness. The cosmic web itself, those delicate filaments we described earlier, the structures that connected all clusters in our current epoch, will have been torn apart. The filaments will have frayed, The junctions will have dissolved. What was once an interconnected structure spanning billions of light years will have become fragmented, isolated, dispersed. Does this sound sorrowful? It need not be. In reality, the processes at work are neither sorrowful nor joyful. They are simply the natural unfolding of physics on the grandest scale. The expansion of space is not driven by some external force pushing things apart. Rather, space itself, according to our current understanding, possesses an intrinsic property, what cosmologists call dark energy, that causes the very fabric of reality to stretch without limit. This stretching is relentless but utterly silent, utterly gentle. It is not a violence, but a gradual loosening, a patient letting go that has been underway since the Big Bang itself. For those clusters that remain gravitationally bound, and many, perhaps most, of the clusters we observe today will persist for trillions of years or longer, the internal dynamics will continue. Galaxies within clusters will continue their slow, stately orbits. Mergers will still occur, but now in ever greater isolation, in clusters that are increasingly cut off from the rest of the cosmic structure. The supermassive black holes at the centers of galaxies will grow and evolve. Stars will be born and will die. The slow transformation of matter into radiation and fundamental particles will proceed according to the laws of physics. But the larger context, the sense of being part of a vast interconnected cosmos, will gradually fade from any perspective. Consider what this means if you allow yourself to reflect on it quietly. The structures we have contemplated in these long moments, the Virgo cluster, with its gentle gravitational embrace, the Coma cluster, with its thousands of galaxies, the great Abell 1689, with its cosmic lenses bending the light of the most distant objects. These will persist. They will endure, but they will do so in increasingly deep isolation. The universe will grow darker around them, not because the clusters themselves will fade, but because everything beyond them will have receded so far that no light from those distant worlds will ever reach them. It is a kind of cosmic forgetting, perhaps. Or perhaps it is simply the universe's way of turning inward, of becoming intimate with its own contents. The dark matter that we inferred through gravitational lensing, that invisible substance that holds these structures together, will remain. Dark matter does not decay. It does not transform into other forms of matter or energy. It will be there, still shaping the gravitational fields of clusters, still keeping thousands of galaxies in their cosmic waltz, long after everything else has vanished from view. In that remote future, dark matter will be the most fundamental feature of existence in any given cluster, the invisible architect, the eternal guardian of structure in an otherwise expanding and thinning universe. And yet, as we have drifted through these vast architectures of matter and time, one of the deepest mysteries astronomers have encountered in recent decades whispers quietly at the edges of everything we have observed about these clusters. The question itself is deceptively simple. If gravity is pulling all these galaxies inward, drawing them together into these massive bound structures, then why does the universe itself continue to expand? And why does that expansion seem to be accelerating rather than slowing? This paradox lies at the heart of something physicists call dark energy, a presence we infer entirely from what we do not see, much as we once inferred dark matter from the invisible hand holding clusters together. Picture it this way. The gravity from all those billions of galaxies in a cluster, all that mass we have traced through the careful bending of starlight, and the orbital motions of galaxies themselves, should be working like a cosmic brake on the universe's expansion, pulling inward, resisting. And yet observations of distant supernovae in the 1990s revealed something unexpected, something that still carries an air of quiet mystery. The universe's expansion was not slowing, it was quickening. Galaxies were being pulled away from one another faster and faster, as if some repulsive force, some negative pressure, was pushing everything apart. We have given this phenomenon a name, but the name itself is a kind of placeholder for our ignorance. Dark energy. What does this have to do with the galaxy clusters we have been observing so gently across these billions of years? Everything, in a way that touches the very foundations of cosmic fate. Clusters exist because gravity has won locally, because the pull of billions of galaxies on one another has overcome the cosmic expansion and bound them into stable structures. But between the clusters, in those vast and emptying voids where no galaxies dwell, dark energy appears to hold sway. The universe is, in a sense, being torn apart along its seams, with dark energy pulling harder and harder at the great filaments that connect the clusters to one another. It is not a violent process. It is slow beyond human comprehension, but it is relentless. This raises a question that cosmologists have been contemplating with increasing quiet concern. What does the far, far future of the universe truly hold? If dark energy continues to dominate, if its strength remains constant or grows, then we must imagine a cosmos billions of years hence, where the clusters themselves have become islands of perfect isolation. The light from one cluster would never reach another. The universe would fragment into isolated islands, separated by impossible distances, each one the only galaxy cluster in an observer's cosmic horizon. Some call this scenario the Big Rip, or heat death of the universe, though these terms carry more drama than the reality likely warrants. In truth, it would be a transformation so gradual, so incomprehensibly slow, that to any observer within a cluster, almost nothing would seem to change. And yet here we are, inside such a cluster ourselves, did you not realize? The Laniakea supercluster that contains our humble local group, that holds the Virgo cluster, which gently gravitationally guides our own galaxy, may itself be slowly fragmenting into cosmic isolation as we speak. We cannot see this happening, of course. The timescales are so vast that billions of years would pass before any perceptible change. But the mathematics of dark energy, the patient equations that describe how the universe expands, suggest that this is precisely what will occur. The comfortable gravitational ties that bind our corner of the cosmos together will, eventually, stretch and weaken as the universe inflates around them. What galaxy clusters reveal to us, then, is something both beautiful and melancholic. They are remnants of a universe in which gravity was far more dominant, where matter clustered and gathered more easily, where the cosmic web was tighter and more densely woven. As the universe has aged and dark energy has begun to assert its curious dominance, the rate at which new structures can form has slowed. The clusters we see around us are, in this sense, late bloomers, among the last great structures that the universe will ever assemble. To look at a distant galaxy cluster is to glimpse a kind of cosmic heritage, evidence of an era when the universe was young enough, dense enough, that such magnificent gatherings were still possible. We do not truly know, it must be said, what dark energy is. Some physicists suggest it may be an intrinsic property of space itself, what Einstein called the cosmological constant, a kind of pressure that exists in the very fabric of reality. Others wonder whether our understanding of gravity itself might be incomplete at the largest scales, whether some modification to Einstein's equations might explain the acceleration without invoking a mysterious new force. Some have even speculated, more tentatively still, that we might live in a multiverse where different regions have different values of dark energy, and that our universe simply happens to be in one where dark energy is just strong enough to allow galaxies and clusters to form, but strong enough too to eventually scatter them again. These ideas remain in the realm of informed speculation, educated guesses about mysteries we have only recently begun to perceive. But what is certain is this: the galaxy clusters, those grand and ancient assemblages of billions of galaxies, are teaching us that the universe is not eternal in its present form. It is not frozen in time. It is engaged in a slow, invisible drama of expansion and separation that will reshape the cosmos over timescales so immense that they strain our ability to truly grasp them. 1 trillion years hence, the universe will look incomprehensibly different. The clusters will have drifted into cosmic solitude. And yet in this knowledge, there is also a strange peace. We are living through a cosmically special moment, an era in which matter still gathers, in which structures still form, in which one cluster can influence and be influenced by another. This uniqueness, this temporary closeness of the cosmos, is perhaps one of the most profound gifts that patient observation has revealed to us. The clusters will not gather again, but they are gathering now, and we are within them, held by their ancient gravity as the universe expands silently around us all. And so, having wandered through billions of years of cosmic assembly, through the silent work of gravity drawing matter together across unimaginable distances, we arrive at stillness. The galaxy clusters continue their patient gathering even now, in this very moment, though the distances are too vast and the timescales too long for any human lifetime to witness the change. Yet there is something profoundly settling in that knowledge, that the universe is engaged in its own slow breathing, and we are held within one small pocket of that vast, gentle motion. Consider your own breath as it moves through you now. Each inhalation draws in the world around you. Each exhalation releases it. In and out, a rhythm so familiar that you scarcely notice it anymore, yet it sustains you with every cycle. This is not so different from the way galaxies draw together through gravity's patient pull. What seems like stillness to us, what appears as a fixed arrangement of ancient lights in the sky, is actually a continuous, unhurried gathering. Billions of galaxies drift together toward a common center, drawn by forces so immense that they reshape the very fabric of space itself. And like your breath, this motion is both invisible and absolute. It simply is, continuing whether we observe it or not. The earliest clusters formed from imperceptibly small ripples in the cosmic microwave background, those faint density variations that physicists detected in the radiation left over from the Big Bang itself. Those whisper-thin undulations became the seeds from which everything followed. And what emerged was not chaos, but a kind of order, a slow, inevitable convergence toward equilibrium. Matter accumulated, stars ignited, galaxies spiraled and merged. Dark matter wove its invisible scaffolding, and through it all, there was no violent urgency, no frantic rushing. There was only the patient accumulation of mass, pulled together by gravity across billions of years as if by some ancient, unhurried hand. When you imagine the Virgo cluster, our nearby gravitational neighbor, gently tugging our own local group in its direction, you might picture it as something happening at this moment, a force acting now. But the truth is even more soothing than that. The influence of that enormous assembly of galaxies has been constant for billions of years, shaping our trajectory through space in a path so gradual that it transcends the human sense of motion entirely. We are being drawn forward, but at a pace so slow that it feels like rest. We are moving, and yet we are still. This is the condition of all things in the cosmos. They are always changing, and yet always the same. The hot gas filling the spaces between galaxies, the intracluster medium that glows in X-rays invisible to our eyes, fills those voids with a kind of warmth, a gentleness that speaks to the security of being held within a gravitational embrace. This gas, too, is slowly settling, cooling across the eons, becoming more organized, more settled. It accumulates in the centers of clusters where the gravity is strongest, drawn downward, like your own body settling into rest, like your muscles releasing their tension as sleep approaches. And the light that reaches us from these distant clusters, this light that has traveled for billions of years through expanding space, carries within it the history of patient assembly. When that light is bent by massive gravity, when it becomes twisted into those ghostly arcs and Einstein rings that telescope reveal, we are seeing the universe's own way of slowing down, of pausing, of showing us the weight of its structures. The light bends because matter has gathered so patiently, so completely, that space itself must curve to accommodate the weight. This is not violence. This is completion. Perhaps there is a rhythm here that your body recognizes, even if your waking mind has not named it. The rhythm of gathering, the rhythm of slow accumulation, the rhythm of things coming together over time, not through force, but through the patient work of simple physics, repeated again and again and again across the expanse of creation. Your own body, as you rest, is engaged in its own form of gathering energy, consolidating memory, drawing together the scattered pieces of consciousness into the coherence of sleep. It is not so different from the way galaxies gather. In the far future, as cosmic expansion carries other structures ever farther away, the clusters themselves will grow lonelier, more isolated, more complete unto themselves. They will have finished, in some sense, their gathering. And there is something restful in that image, the thought of structures that have finished their becoming, that have settled into what they are. As the universe expands and cools around them, these islands of matter will become even more self-contained, even more at peace with their own immensity. The light years that separate the galaxies within a cluster might seem to speak of distance and loneliness, yet they instead testify to a kind of togetherness, a gravity so strong, so persistent, that it holds these structures together against the expansion of the universe itself. They remain connected. They remain gathered. They remain part of something larger than themselves. And so you, too, are part of something larger. You exist within the Laniakea supercluster, within the cosmic web, within a universe that has spent 13.8 billion years gathering itself into patterns and structures and light. Your every atom was forged in stars that existed within galaxies, that joined in clusters that eventually coalesced into the vast networks we observe today. You are not separate from this process. You are its product. You are its continuation. You are the universe becoming aware of itself through the gentle gathering of consciousness into the stillness of sleep. As your breath continues its patient rhythm, as your thoughts begin to dissolve into the quieter realm of dreams, know that you are mirroring the cosmos itself. Inhalation and exhalation, like the contraction and expansion of space. Gathering and releasing, like the patient assembly of galaxies across time. And in this moment of rest, you are not removed from the universe's slow work. You are participant in it. You are held, as surely as any galaxy is held by gravity, within the warm and patient embrace of a cosmos that knows, above all else, how to gather things gently together and let them settle into peace.